Hey guys, it's me. So join me, cartoon me, as we talk about the periodic table of elements and water. So remember, water is made up of hydrogen, which has one electron, so one valence electron, one electron to bond with, and oxygen, which has eight electrons, so six valence electrons, two of which will bond with each other. So here's our oxygen. So we have two oxygen atoms and they bind together to make oxygen in the air, O2. You can see that they bind with two valence electrons together that's covalently bonded, just like hydrogen bonds together. They are covalently bonded together with their each valence electron. So let's learn more about oxygen. So oxygen is a colorless, odorless gas that's all around us. It's also highly reactive. That means that it's reactive in the air around us, it's reactive with each other, and it's reactive with water. And it's made by plants through the sun, and it's made through photosynthesis. We also have hydrogen. Hydrogen is also a colorless, odorless gas. It is also extremely flammable. This is why we don't have hydrogen gas balloons anymore, like air balloons that people would fly in. It's also the most common element in the universe. Now, these come together to make water. So we take our hydrogen and they split apart with our oxygen, which splits apart, and each oxygen atom gets two hydrogen. Woohoo! And we just made water. But wait a second, we have four hydrogen atoms. How'd that happen? So if we look at our chemical equation, we need two molecules of H2. So we need four atoms of hydrogen so that we can bond with one molecule of oxygen or two atoms of oxygen. That way we can get our two water molecules. So that way each oxygen has two hydrogen and we get two waters. And there is water. Yay! Our molecule of water is made, and water is amazing. It's a liquid, unlike its gas counterparts of hydrogen and oxygen. Water also has the unique ability of high surface tension, and it's also necessary for life. Water, amazing substance. So, goodbye, guys. Next, we are going to look at the states of matter with water. See you there. Oh, hey, everybody. I'm not in animation form. So join me as we look at the states of matter using this wonderful simulation by PhET Interactives. And we're going to look at the states of matter. So let's dive on in to these states. So if you notice, you're looking at different atoms and molecules. We have neon, argon, oxygen, and water. We just talked about oxygen and water. So let's talk about neon and argon. Neon is a gas, and it's also used in neon lighting, if you didn't know. It's also a noble gas. That just means it's not reactive. It means that all of its outer valence electrons are already filled. They're already paired with each other, so they don't really want to bond with anything else. And we're able to get neon through liquefying air. Argon is also a gas, and it's also a noble gas. Also, as a known fact, it's the third most abundant gas, but it's actually rare in the atmosphere. Less than 1% is in the atmosphere. And argon is used in fluorescent lights, and it's also used in historical preservation. That way, instead of oxygen, where it can actually damage the paper, argon, since it's not very reactive or not reactive, they use that to be able to preserve the paper so it doesn't degrade. So let's kind of take a good look at this simulation. So we're looking at solids, liquids, and gases. So let's look at solids first. So solids of neon, if we notice this is a solid, and even if we bring the temperature down even more, we notice that molecules are actually moving, right? They're vibrating a little bit. Let's look at argon. Argon, same thing. And same thing as neon too. If we notice, both of them are in a cube shape. They're not changing shape at all. But the molecules within it are vibrating, they're shaking. Let's look at oxygen. Now, oxygen, as we notice, oxygen binds with each other when it's by itself and not part of water and in the atmosphere. So here is oxygen. They too are vibrating and shaking. Now let's look at water and see what that looks like. So let me change the temperature gauge here. So at negative 127 degrees Celsius, that is a negative 196.6 degrees Fahrenheit. Oof, that's cold. And here we can see the water, it's taking still a definitive shape. So we see that the molecules are tightly packed. The water, not as tightly packed as, say, oxygen and argon and neon, And we can see that because all of these different molecules are a little bit different from each other. And so the water, because of the molecular structure, they aren't able to get as tightly packed as oxygen. But they're still tightly packed, and they still take a definitive shape. And even as I cool it more to make it more colder, really, to make it more of a solid, not really possible. But as we can see, as we cool it down, it stops vibrating as much. It's still vibrating. It still shakes a little bit. So these are facts of solids. Solids, they are moving, but they're not moving much. They keep a fairly specific shape on their own. So they have a definitive shape, they have a definitive volume. That means that their shape doesn't really change and their volume doesn't change. So yes, solids can change shape, but mainly if something's done with them, like you do a physical change. So like, chopping wood, you're changing the shape, but because you're actually chopping it in half, but it still kind of keeps its definitive shape. Solids also have a very high density and they're also slightly compressible, meaning that you can kind of push it down a little bit sometimes. Now let's look at it in liquid form. So liquid, if you notice, our temperature went up. So we are now at 13 degrees Celsius or 55.4 degrees Fahrenheit. We can see that the particles, they're more loosely packed. They're not as tightly packed as they were, say, as a solid. They are a little bit more loose. They're also able to flow around each other. As you notice, they're moving a lot more than they are as a solid. And the shape's not really definitive. As you can kind of see, we got one kind of popping up and down right there, and it's kind of moving all around. And you know this from experience when you drink something, it doesn't really have a definitive shape. And that is one fact about liquids. They don't have a definitive shape, meaning they take whatever shape of the container that they are in, but it has a definitive volume. So there's always a volume to a liquid. Also, they have mid to high density, so they're a little bit less dense than, say, solids are. And they're also slightly compressible, meaning you can also kind of press that down. Let's look at gases next. Look, our temperature increased to 156 degrees Celsius. That is about 312 degrees Fahrenheit, pretty hot. So as you notice now, there's a lot of space between the molecules, and they are going crazy. They're moving super fast, they're moving faster than before. They have a lot of movement, they have a lot of energy, a lot of kinetic energy, really. And so if they have a lot of movement with all this energy, they got that energy from adding heat to it. So that heat energy was transferred to kinetic energy. If we notice, there's no definitive shape to this. There's no shape anymore. They're just chaotically springing around. So if they left unconfined, if I open this container, then the gas will spread out. We can't really keep it. So it doesn't have a definitive shape. It doesn't have a definitive volume. And it also has a very low density, and it's very compressible, highly compressible. That means it's just very easy to push together because I can compress all of that gas into a smaller space if I want to because it has all the space in between. So let's look through that again. So let's look at it again as a solid. Maybe let's look at it as an oxygen. So here we get out as a solid. The particles have fixed locations and they're attracted to each other as a definitive shape and a definitive volume. Now let's add a little bit of heat to this. As we add heat, the particles are still attracted to each other, but they just move around a little bit more and they become a little bit looser. As we kind of get through that, look at them kind of go together. They're still attracted to each other. They're still trying to kind of take like almost a definitive shape, but they're not quite able to. But they are containing a definitive volume. They're moving a little bit more. And if we add some more heat, we're going to get some more action. So as we add heat energy or thermal energy, now that's being transferred to the molecules and that's being transferred to kinetic energy, meaning the motion of the particles. They're moving around a lot more as they become a gas. They have so much energy and motion that these molecules just don't care where they go. They're just flying everywhere. It's this random motion. The motion of one particle is unaffected by the motion of another particle. So like this particle right here isn't moving in this direction because of any other particle unless it bounces off of each other. That's really it. So that is our review of solids, liquids, and gases. So next, I'm going to talk about plasma. So I'll see you out in the living room, really, the main staging area, as I talk about plasma. I will see you later.
All right, before I say goodbye to today's episode, we got to talk about plasma, that fourth state of matter that we have not discussed yet. So plasma is kind of like a gas, but the atoms are a little bit different, and I'll show you what that looks like in just a second. Plasma is also not very common on Earth. We only kind of see it in a few things and we can make it, but it's incredibly common throughout the universe, just not here on Earth, which is probably a good thing because it takes a lot of energy to be able to create them. So examples of plasma would be like created through lightning. We wouldn't want lightning happening all the time. Solar wind from the sun, which helps create the aurora borealis. We can make that again, like I said, in fluorescent lights, and it also occurs in nuclear fireballs. This is the northern lights, the aurora borealis. This is what we see where the phenomenon of plasma, where these electrons and these protons are kind of floating around. We also see this created in what's called plasma balls, the fun things that you can have in your rooms. So what this looks like, and what I had said was, it's this floating around of like basically the nucleus, protons and electrons. What I mean by that is this. So we have our solid, liquid, and gases. Our solids, when we add some heat to it and melt it down, we kind of like loosen the bonds, create some more energy like we said, and we get this more free-flowing liquid where their atoms and the molecules are still kind of like bonded and stuck to each other. As we add more heat, it turns to a gas, and now they're just bouncing around everywhere and kind of haphazardly. And then as we add an enormous amount of heat and we go through like basically ionization is what it's called, and what happens is where we strip off the electrons. So if this is our atom, we are stripping off the electrons to this atom to where they're now just kind of floating around, and that's creating this plasma that we see in neon signs. That is plasma. So it's like basically, again, how we create it through fluorescent lights is just electricity runs through that long tube where there is a gas and it just strips off those electrons. All right, that is it for tonight, or well, not tonight, for me it's tonight. That is it for today's show. So reminder, each element and compound is different from their properties. We looked at several of those. We looked at neon, we looked at water, we looked at oxygen. We are surrounded by these incredible phenomena every single day, by all of this matter, by all of this energy, and by all these different states of matter. It's in our hair, it's in our hands, it's in our faces, it's in our pets, and it's in you. It's in everything. So, some of you had said that you wanted to learn more about the periodic table of elements, so I hope you enjoy this music video, or video of music, by these guys called ASAP Science. They are singing all about the different elements and where they can be found. Enjoy them. Take it away, ASAP.